So the complex number system is a number system which is outside of any numbers that we've used so far. So we've always worked in the real number system with our integers and our rational numbers and all that kind of stuff, but we've never kind of ventured outside that. So complex numbers is actually the outside the bubble, even bigger than that. So complex numbers actually include all real numbers. So the complex part of a complex number is the I component, and where I has come from is that we previously didn't really have the ability to talk about when the discriminant was smaller than 0. So what we're doing by using complex numbers is essentially we're just making it so we're actually able to do that. And how we're able to do that is by making I squared equivalent to -1. So that's what we get. And then so when we try and make a complex number, we have an imaginary component and a real component. So the imaginary component can be 0 and the real component can also be 0. So it can be 0 plus 0i, right? Or it can be 0 plus 3i, or it can be 3 plus 0i. All of those would still be defined as complex numbers. So the real important thing is that the coefficients of complex numbers must be real. So you can't have I plus I squared I. Like, that doesn't really make sense. It's going to simplify to it's going to always be simplifiable to either it's always going to be simplifiable, so there's a real component and an imaginary component. So we just really need to be like that's just one thing that always needs to be true. The coefficients always just need to be real numbers. Cool. Alright, so for the imaginary number, so for the complex number, z equals to a plus bi, well, there's two components like we talked about. There's the real component and the imaginary component, right? So because the coefficients are real, we can just say, if we're talking about the real component and the imaginary component, they are just the coefficients of the numbers, right? They're not bi, it's just b, because it's just talking about the coefficient of them rather than the whole thing. Okay, so let's go through a couple of the things that happen in complex numbers. So the first of all is it's kind of just like learning a new universe of numbers, right? That we've previously done, and now we're going to venture into further. We can apply most of the algebra rules, because remember, real numbers are complex numbers. So most of the rules that apply to real numbers, we can kind of extend and change a little bit so that it becomes applicable to complex numbers as well. So essentially what we can do here is if we were pretending this was a real number, so if we had a plus b squared, we could simply expand that to a squared plus 2ab plus b squared, right? So what we're going to do here is we can do the same thing. We're going to have 4i squared plus 12i plus 9, right? So that's kind of the result we're going to have. The extra step we have to take in terms of complex numbers is simplifying it to make sure that we have a real component and an imaginary component. So in a complex number, you should really only have two segments to the question, right? Or as in, you should have just two parts. Like, we shouldn't have three things with different like I coefficients. It always should be simplifiable to two parts, because this one, for our I squared, remember the whole idea of it was I squared is equivalent to -1. So we're just going to get -4 plus 12i plus 9 here, which is equivalent just to 5 plus 12i. Okay, amazing. Alright, let's talk about this one. So a little bit more trickier this time. So we still do what we normally do in the universe of this. So we'll get that this is going to be I to the power of 5, right? So we're falling across. So I to the power of 5, then plus I to the power of 3. Now we're going to do this one. So -5i times I cubed is going to be -5i to the power of 4. And -5i times I is going to be just -5i squared. So we're going to get that equation. Now, I is just equivalent to I squared, we talked about how that's the basis of everything. It's just -1. Now, I cubed is going to just be equivalent to I squared times I, right? So it's going to give us -I. And then I to the power of 4 is essentially just I squared. And -1 squared is just 1. And we can kind of always use it from there. So we can kind of build a basis. So if we have I to the power of 2n, right? That's going to be just equivalent to -1, right? If we have I to the power of 3n, that's going to be equivalent to -in. So in. If we have I to the power of 4n, that's going to just be equivalent to in. Oh, sorry, 1n. Let me just rub that out so it's a bit cleaner. So what we get from this is I to the power of 2n, or is just equivalent to 1 to the power of n. If we have this, we have -I to the power of n. If we have this, it's going to just be equivalent to 1 to the power of n, right? So if we had I to the power of 8, it would just be I to the power of, I to the power of 2, and then just square it again. So I to the power of 4 squared, which is just 1, right? Still 1. But in all, these are kind of the rules that we can use. So whenever we have this, we kind of try and decompose it so it's in terms of one of these, right? So what I to the power of 5, we can change that to I to the power of 4 times I, right? I to the power of 3, we already know what that is. It's going to be -I. 5I to the power of 4, we know what I to the power of 4 is. It's just 1. And I squared, we also know what that is. It's just going to be -1, right? So what we're going to get here is I to the power of 4 is -I, and then we get -I here. Sorry, positive I, not -I. Positive I, right? Because the I to the power of 4 is just I. And then, sorry, I to the power of 4 times I is just I. And then we get +I, minus 5, plus 5. So all in all, we can see everything cancels out, and we're just going to get 0. So that is my expand and simplifying. So it all simplifies to 0 here. Alright. So then we realize the fractions. So realizing fractions is kind of like rationalizing a surd. So you know how when you try and rationalize a surd, you have something like, I don't know, √2 plus 3 over 1 minus √2, and they want you to rationalize it. So what you can do is you can go √3 plus 1 minus √2, and you can times that top part by the conjugate of it. So you get that, and you can kind of times it across, and you'll just get that it's going to be √2 plus √2 squared, so that's 2, plus 3 √2, right? And that's going to be all over I squared minus √2 squared. So we'll essentially get that this is going to be 2 plus, so that's going to be 4 √2 plus 5. So we'll get 5 plus 4 √2, and that will be 2 squared, right? So we'll just get that's all over -1, so we'll get a negative version of that, right? So that's what it's going to be equivalent to. It's the exact same thing as what we're doing here. So when we have I plus 3 over 2I minus 1, we times it by something called the conjugate of it. Now, the conjugate of it, if we have x plus iy equals to z, the conjugate of that is now going to be x minus iy, right? So it's just changing the imaginary component, negating that. So we can times that by 2i. Yeah, we can times it by 2i plus 1 as well. Well, maybe let's not do that. I mean, it still is possible, right? But I guess by convention, we can just talk about times by its conjugate. Because even with 2i plus 1, it should still give you the same result. The real thing is that we need a difference of products of some sort. So it's going to be -1 plus 2i, -1 minus 2i over -1 minus 2i. So it's entirely possible just to also times this by 2i plus 1 as well, because it would give you the same result, because the main thing is that you just don't want any remaining i's at the bottom. But let's just do it this way for convention's sake. So when we times that across, we'll get this as I plus 3 times -1 minus 2i, and that's going to be all over -1 squared minus 2i squared, right? So when we kind of put that across, we'll get that this top part is going to be I minus 2i squared minus 3 minus 6i, right? So we can kind of get that, and then this will be all over 1 minus 4i squared, so i.e. 1 plus 4, because remember this cancels out to negative 1. So we'll get that if we kind of group like terms here, and remember I squared equals to negative 1, so we'll just get that it's going to be negative I plus 2 minus 3 minus 6i over 1 plus 4. So we can group everything now, so we'll just get that this is going to be negative 1 minus 7i over 5. And that's going to be our overall answer. So it's essentially just doing what we normally do with surds anyway, and just rationalizing it using that. Cool. Alright, so let's talk about solving. So just like how we solve for normal quadratic equations and solve for normal polynomials, we can kind of apply the same methods here. Evidently this, right, the discriminant is smaller than 0, because we essentially just have 0 squared minus 4, 1, 64, which is evidently going to be smaller than 0. So this is why it says solve over C. So if it doesn't say solve over C, so we really need to keep our eyes peeled for whether something says solve over C or not solve over C. Because if it says just solve over, like x belongs to R or something like that, then we wouldn't be, even though we might know about complex numbers and we know how to utilize them and all that kind of stuff, we're still not going to use them because they're asking for only real answers. Now, if they asked for complex numbers, like in this question, an important thing to do is solve for the complex ones. So what we can do is utilize our knowledge and kind of introduce that there. So instead of writing x squared plus 64, what we're going to write is x squared minus 64 I squared, and that equals to 0. So now that we have it in this form, we can apply the DOPS thing of a squared minus b squared is equivalent just to a minus b, a plus b, right? So what we can go here is x minus I, x plus I is equivalent to 0. So therefore we will get that x will equal to 8i, or x will equal to negative 8i as our solutions. And that one, that's just how you do it. That's all you need to do. So just make sure that they're asking you to solve over complex numbers rather than just the real numbers. Okay, amazing. So let's kind of extend that further to doing something like this, where it's a little bit less straightforward. So once again, we just check the discriminant quickly. So once again, b squared minus 4ac. So it's going to be 2 squared minus 4, 1, 5, which is going to be equivalent to 4 minus 20, which is negative 16. So that's smaller than 0, so we're unhappy with that, so we can't solve for real numbers. But we can try for complex numbers. Now, the question is, where do we introduce our I squared? And we're going to use our smart little noggins and know that we can actually change this into another form where we normally actually do the DOPS products from, right? There is not really a way that we can factorize it straight, unfortunately, so we have to just use a bit of our DOPS products and do a special process called complete the square, which you all will be quite familiar with from doing in polynomials and doing it in methods as well. So when we try and complete the square, what we try and do is we look at the x term, we half it, so 1, and square it, so 1 squared, and then we minus as well, right? Because we can't just add random things. We need to actually make sure that we're compensating for it. And then we can plus 5 at the end because we're not changing that. So that's equivalent to 0. Right. So then we grab the first 3 terms because now that's the perfect square. So we'll have x plus 1 squared plus 4 is equal to 0. Now, once again, we can see if we put this to the other side, it would be negative, right? So we'd have x plus 1 squared equals to negative 4. So what we're going to do here now is essentially when we have this negative 4, we can now change it to 4i squared, okay? So we're going to have x plus 1 squared equals to 4i squared, right? So therefore we can kind of have a look here, and now that we have this 4i squared instead of this negative 4 on the other side, we can actually solve for this. So we'll have x plus 1 squared here, and essentially we can now try and plus or minus it, right? So we'll have x plus 1 will equal to the plus or minus of root of 4i squared. Now 4 can be rooted to 2 and I squared can just be rooted to 1. So we'll have x plus 1 equals to 2i, right? Plus or minus 2i. So we'll have that x will equal to -1 plus or minus 2i. And this is where sneaky, something called the conjugate root theorem kind of sneaks in. So what the conjugate root theorem is that if we have something like ax squared plus bx plus c, and this applies for any polynomial, not just when we're considering quadratics, it applies for any polynomial in the universe. If a, b, c all belong to R, and we're solving over a complex plane, if there is one complex root, there must be another complex root, right? And that's just to compensate, because if you don't have two complex roots, you'll never be able to return to real coefficients. So that's why, in order to compensate for that, the roots must be conjugates of each other. So that just means that if you have a root -1 minus 2i, and they've told you that, and you can see that they're all real coefficients, our other root must be -1 plus 2i. Cool. Alright, so let's keep on going with this. So we now have x squared plus 2a equals to 0. So what we can do here is now we'll do the same thing. We don't really know what 2a is, but that's okay. Yeah, we assume that a is probably bigger than 0, so that's why it doesn't really matter what a is, right? Or if this was a negative, then if a was a negative number, technically you wouldn't really need to do complex, but we're assuming a is bigger than 0. Otherwise, why would they be asking us to solve a complex? So we can change this to x squared minus 2i squared equals to 0. So once again, we can factorize it into the two forms. So x squared minus root 2a squared, x plus our root 2ai squared. So essentially we're going to get x minus 2i 2a and x plus I 2a. Note, in terms of kind of solving and doing stuff with your complex numbers, your I should never really be left in an equation. So it shouldn't really be left as a squared cube like we saw before. We can simplify it further. It also shouldn't be left under square roots as well. So if you find that you can't get your I out of the square root or something, just, sometimes it is like that, but it's kind of quite rare. So if that does happen, just be a bit careful and just make sure to recheck your working out to make sure it looks like everything looks reasonable. Okay, so that was the Cartesian form that we were playing with a little bit, and there's another form called the polar form. So where the Cartesian form is kind of talking about coordinates, where we're talking about longitude and latitude, the polar form is talking about how far we're going and what angle we're going. So it's kind of like going 30 degrees to the north for 400 meters. That's essentially what a polar form is telling you. It's telling you how far to go and what the direction is to go. Whereas the Cartesian plane is kind of pinpointing where the position is. So we also represent it via this thing called the Argand diagram. So whereas we have the Cartesian plane for real numbers, we have something called the Argand diagram for complex numbers in general. And we just replace the axes with real component, imaginary component, because it's x plus iy in terms of z. So our x kind of corresponds to our real component and our imaginary component kind of corresponds to our y. So that's how we can kind of represent it. And what we do is we represent it as r cis theta. So r will tell you how far it is from the center, and cis theta will tell you the direction where it's going in. So theta will tell you the direction, and it's always measured anti-clockwise from x-axis, and hopefully it will ring a little bit of bells in terms of why it is like that. And why it is like that is because, remember, for our circular functions and all that stuff that we're working with, because complex numbers, the polar form is kind of represented from circular functions as we can use so that it's transferable across, I guess. It's done in the same way, because in terms of circular functions, it's always measured anti-clockwise from the positive direction of the x-axis. In our equation that we have here, it's also, in our complex numbers that we have here, it's also measured from anti-clockwise from the positive x direction. Cool. Alright, so then that kind of represents that. The next part is our absolute value, otherwise known, it can also be represented like this. So might seem a bit familiar from when we're doing modulus functions or absolute value functions. So that's our R component, and it's just a squared plus b squared. Hopefully this also rings some bells, because if we know this is a plus bi, we can see there a, b, you know, Pythagate, so you have a squared plus b squared, and then root it to get the third side. Okay, so essentially from our knowledge of angles, we know that theta equals to 2 pi k, right? For if we have just a normal, like without any like changes in the period, it's going to repeat every 2 pi k. Now, because if we said we were repeating at 2 pi k, so if we go back to here, right, and we talk about r cis theta, there would be thousands of angles which would represent the same direction, right? Because of the repeating periods that we have for circular functions. So rather than doing that, because mathematicians hate when we have multiple answers for the same thing, we have to give them a range of values which there's no repeating, right? Arbitrarily, they kind of just chose negative pi to theta, negative pi to pi, and it's important to note that it's the pi which is included rather than the negative pi. So if you get a solution which is negative pi, you need to make sure to exclude that one as well. So your arguments in terms of your solutions and everything, it must be within this domain. Sometimes they'll ask for a lowercase arg in which you might get away with being outside the domain. But I would say it's always safest to try and keep your answers within this domain, and this can be represented by the capital. So the capital versus the lowercase, the capital actually refers to this domain for the angle, whereas the lowercase doesn't. But I would just be really careful, because especially when you're solving, you'll always be solving for this domain. Okay. In terms of multiplication and division, so previously we would have done, you know, kind of how we did a bit of expansion, we did the FOIL, it was okay, but like it can get pretty complicated evidently. So imagine if you had something like root 3 plus 4i times 17, or not 17, like 7 over 2i plus 5 over 2, and like imagine if you had to do that, it would be okay, it would be doable, but it would just be a bit gross to do, right? So our alternative to make that less gross to do is to use a polar number. So how we can use our polar number is essentially we'll have z1 times z2 will give us r1 r2 times our cis1 minus our cis2. So this should be cis1 plus our cis2. So we add the angles and we multiply those, and when we divide the r component, so we divide the modulus and minus the angles. So one thing that's really important to kind of note is that like these formulas, right? We look at them and we're like, yep, they look okay, they look reasonable, yeah? Where do they actually come from? So where do they come from will be only answered when you learn about all the different circular function theorems and stuff like that. So once you are able to have a bit of a chat about that and understand the circular function theorems, particularly the addition of angles, I would encourage you to revisit these concepts and try to actually prove these, because they have been known to be questions from VCA and things in the past. So I would recommend maybe coming back to it and just making sure you know how to prove these relations. Cool. Alright, so let's talk about first converting things to polar. So if we try to convert things to polar, the first thing that we want to do, I like to do it this way, where we kind of like break it up into segments. So when we try and break it up into segments, what we'll have is that we'll have the r component and we'll have the theta component, right? So what we can have here is the r component. Remember, we said that's just the modulus of z, which is otherwise known as a squared plus b squared. So in terms of our polar number, remember it's I, so it's going to be 1, this is going to be I. So we can kind of say, oh, okay, so it's going to be approximately there. So we can kind of see that it's just going to be root 1 squared plus 1 squared, which is going to just be root 2. All right, so then our theta. Our theta is best found via going tan inverse of our y over our x component. So tan inverse of that we'll be thinking 1 over 1, so it will be tan inverse of 1. Now, the only catch is that we need to tell them which quadrant it's in, because remember, for any angle that we find, tan, it could be in, so for positive ones, it could be in this quadrant, or in this quadrant, if we're talking about negative things. So how would we be able to predict this? And the answer is, we kind of just look back to the equation that we're trying to convert, right? So it's 1 plus I, which means that both of these are positive, right? So that means x is greater than 0 and y is greater than 0. So what that tells us is that it must be in this quadrant right here. So therefore, we're going to just be using the first angle, and we think, okay, when does tan equal to 1? And we think, okay, that's when we have 1 root 2, otherwise known as the pi and 4 triangle. So we know that theta will therefore equal to pi and 4. So then we kind of collate that all together, and we'll say 1 plus I, and we put that together, so it's root 2 cis pi on 4. And by the way, the expression of cis, because people are often a bit curious about where cis comes from, or there's nothing explaining here, so I'll just write it out on this slide. Cis actually just represents root 2 cos pi and 4 plus I sine, what did I just do? I sine pi on 4, and it's this part and this part, which is the cis, so it's kind of like an abbreviation of it, essentially. Right, okay, so let's try and convert this one to polar now. So once again, we start off by breaking apart into two parts. So we break it apart into the r component and the theta component. So the r will equal to root of negative 3 squared plus 3 squared, which is going to give us 3 plus 9, which gives us 12. So that's going to just be 2 root 3. And that's going to be our root that we're talking about. Alright. So then what we're going to do is we're going to try and find the other part of it now. So tan inverse of 3 over negative root 3, that's going to give us that's the tan inverse of negative root 3. We think of when tan is equivalent to negative root 3 and build up our triangle. So now we want the root 3, 1, 2 triangle, and it's opposite over adjacent, so we must be looking at this angle up here, so pi on 3. So therefore, we're going to be considering this as our pi on 3 angle. But remember, we look at the quadrant. This is negative. That means it's either in this quadrant or this quadrant. We look at our components. X is smaller than 0. Y is bigger than 0. So therefore, it must be in this one here, right here. So therefore, we're going to say, so our base angle that we want is pi on 3. And it's in the second quad, right? So it's going to be pi minus pi on 3, otherwise known as 2 pi on 3. Okay, cool. So then once again, we piece it all together. We get negative root 3 plus 3i will equal to 2 root 3 cis 2 pi on 3. Okie dokie. Amazing. Alright, so let's get moving on again. So next we want to convert negative 13. So like I said, all real numbers are complex numbers. So even if you don't have an imaginary component, you can still consider it a complex number because you're still able to convert it into the different forms. Like this is essentially just 13 plus I, like plus 0i, right? And there's not really much difference compared to that. Cool, awesome. So then therefore, what we can do here is we can kind of look into this one. So once again, we can split it into the real and the r, so the modulus, and also the theta part of it. So what we can do is we can kind of split this up, and we'll say that this is going to be r is going to equal to the modulus of z, which is equal to root a plus b, and we know that it's kind of on the axis actually instead. So it's actually right here. That's where, oopsies, no, not there. Right there. That's where probably the angle is. That's probably where the polar number is. Ignore that. I'm going to rub that out so that we don't get confused. So it's actually right there. That's where we're looking at. Okay, so therefore we can write this as root negative 13 squared plus 0 squared. So it's just going to be 13. And then we can talk about theta. So theta is tan inverse of 0 over negative 13, so that's going to be tan inverse of 0. And we think to ourselves, okay, when does tan equal to 0 in terms of our unit circle? So, and in terms of just things in general. So that will mean that the sine equals to 0, so it must be along this axis, and that the sine equals to 0, so that must mean that it's along this axis. So it could either be here or it could either be here, right? Then once again we look back into our equation. So we note that the x part is negative, so that must mean that it's on this side of the thing. So if we kind of do a bit of a cross section, we notice that it must be here rather than the one here, because x should be positive on that one. So we know that now, therefore we would have pi as the angle. So when we write this out, this is going to just be equivalent to 13 cis pi. And look, it looks so much more complicated written like this compared to this, but it's just one difference of writing it into polar form. Alrighty, okay. So now let's talk about going in the other direction, and I think that the other direction is actually a bit simpler because you don't really need to break it up. You can kind of just do it a bit straight, and it kind of goes sequentially down rather than having to break it apart and then put it back together. So what we can do here is we essentially just rewrite this as negative 4 cos 2 pi on 3 plus I sine 2 pi on 3. And then what we're going to get here is that it's going to be negative 4, right? And then once again, we have to check our angle. So our base angle that we're working with is pi on 3, which is this angle here. Remember, our triangle is root 3, 2, 1, because it's hotchard out of a 2, 2, 2 triangle. So we know that it's going to be, so in terms of our cos, it's going to be 1 over 2, right? Because we can see that it's adjacent over hypotenuse, so it's going to be 1 over 2. And then our sine, so plus I, our sine is going to be root 3 on 2, because we can see opposite over hypotenuse, so root 3 on 2. Okay, the second part of this is we once again need to consider what quadrant we're working in. So 2 pi and 3 is going to be in the second quadrant, and we can see y, or the imaginary component, is going to be bigger than 0, but the real component of z is going to be smaller than 0. So this part should be negative, so we'll get negative a half, and we'll just get positive version of this, right? Okay, so then we kind of simplify it and make sure it looks nice, so we'll get negative 4, negative a half, root 3, sorry, this is just times, that looks like a plus instead, root 3 on I, and then we can times the 4 out as well, so we'll just get 2 minus 2 root 3i, and that's our Cartesian form. Cool. Alright, so we can kind of repeat the same here, except for our, now it's square root 2, so once again we expand everything out, we get square root 2 cos 3 pi on 4 plus I sine 3 pi on 4. And this time we can check, maybe do the check before so it's a bit neater. So once again, 3 pi on 4 is in this quadrant. We do our triangle for pi on 4. So that's 1, 1, root 2. And we can see it's 1 over root 2 and 1 over root 2. Or alternatively, so it's 1 over root 2. Or you can write it as root 2 over 2, which might be preferable here given that, like, we can check which one's preferable. If there was a 2 on the outside, I might go with this one. But because there's a root 2 on the outside, I might actually go with this one, so it cancels out. Once again, we see that cos is negative, so we're going to have root 2 times negative 1 over root 2. And sine is positive, so we're going to have plus I over root 2. And then we can kind of times the root 2 out. So we'll just get this as negative 1 plus I. And it's completed. So we can kind of tell which quadrant it is by which one's positive and which one's negative, and either back or forth you can kind of always tell what quadrant a complex number is going to lie in. And like, even if we were doing this via a Cartesian form, so this should be negative 1, 1, you can kind of see what quadrant it is when you try and graph it out as well. Okay, so now that we've talked about how to convert polar to Cartesian and Cartesian to polar, let's now chat about actually doing it and doing this complex multiplication. So essentially it's always easier in polar, and I want you all to remember that. Even if like you have to convert to polar and then convert back, I'd still recommend it because I just find it's so much easier and just so much cleaner as well, because the more you do, the more you are prone to making mistakes. So I just find if you convert it once and then do all the stuff and then convert it back, it's often a lot nicer. Okay, so Z1, Z2 is going to be equivalent to R1, R2 cos theta 1 plus theta 2. So what we're going to do, so Z1, Z2 here is 7 times 6. Cos theta is going to be pi on 3 plus pi on 2. Now, the real trick here is that this, right, because this is 3 pi on 6, and this part is 2 pi on 6, right? So this all stays under our equation. But, for example, if we had 2 pi on 3 plus pi on 2, you would note that that's going to be outside, because our domain goes from here to here, right? And then here to here, yeah? And it doesn't include that point at the end. So if this was 2 pi and 3, instead of just pi and 3, we would actually need to exclude a value at the end. So we would have to go backwards. So if this was 2 pi and 3 plus pi and 2, we would have to find the angle and add the angle up, and then we would have to find the corresponding angle in the domain of this domain, right? Because we want our capital R. But for this one, it's not much of an issue, so we can just say that's 42, cos this is 2 pi on 6, and this is plus 3 pi on 6. So we'll get that this is going to be equivalent to 42 cos 5 pi on 6. And sometimes they'll get you to convert it back into a Cartesian form, and if that's the case, once again, we can kind of figure out the quadrant. So once again, it's going to be in this quadrant, and for now we're looking at pi on 6. We're going to use our root 3, 2, 1 triangle, and then we're going to just get that's going to be 42 on the outside. Our cos 5 pi on 6 plus our I sine 5 pi on 6, and we'll get that this is going to be equivalent to 42. Our cos 5 pi on 6 is going to be equivalent to root 3 on 2, right? And it's going to be negative since the quadrant, root 3 on 2. And our sine is going to be positive, and it's going to just be a half. So plus a half I. And then if we kind of expand that out, it's going to be negative 21 root 3 plus 21I. Cool. Awesome. All right, so let's talk about dividing those two now. So it's Z1 divided by Z2. So we're going to have, remember we know that that's going to be R1 over R2 cis theta 1 minus theta 2. Now what we're going to do is just put that all in. So if we have Z1 over Z2, what that's going to be equivalent is R1, so X, so 7 over 6, right? So cis therefore will be pi on 3 minus pi on 2, and we'll get that this is going to be 7 over 6 cis of, so that's 2 pi on 6, 2 pi on 6 minus 3 pi on 6, so we'll get that this is going to be 7 over 6 cis negative pi on 6. And once again, if we wanted to kind of convert to polar again here, we could make this 7 pi on 6, and we could kind of expand that out. So it would be cos negative pi on 6 plus I sine negative pi on 6. So think of the quadrant, negative pi on 6 is here. Think of the triangle, once again, it's the root 3, 1, 2 triangle for pi on 6. So we're going to write this out as, now our cos is positive, so 7 over 6 is going to be 1, it's going to be root 3 on 2, and our sine is going to be a half, so it's going to be negative a half though, because of the quadrant. So then if we kind of expand that out, we would get that this is going to be 7 root 3 over 12 minus 7 over 12i. Cool. Awesome. All right. So let's now try the other way around. So now we want R2 over R1 cis theta 2 minus theta 1. And it's important to know which one's which, right? Because for our multiplication, it doesn't really matter which one's which. But for division, it does, because one divided by the other and the other divided by the one, it's not going to be the same thing, right? It's kind of like 5 over 4 is not the same as 4 over 5. So that's why we need to just be a little bit more careful. But 4 times 5 and 5 times 4 is going to be the same thing. So therefore what we can do is therefore we can write this out. So we'll have this is going to be 6 over 7 cis of pi on 2 minus pi on 3, which will give us 6 on 7 cis 3 pi on 6 minus 2 pi on 6, which is going to be equivalent to 6 over 7 cis pi on 6. Once again, we can do our conversion to, so this is only if they ask you to convert to Cartesian, otherwise you can just leave it, but I thought, might as well take the extra step so we can go through it together. So now it's in the first quadrant, and in terms of our triangle, once again it's the pi on 6 one, so our color in the angle, I'm going for root 3, 1, 2, so we all know that that's going to be 6 on 7 cos of pi on 6 plus I sine pi on 6, and that's going to be 6 on 7, therefore pi on 6 is going to be root 3 on 2, and our pi on 6 here will just be a half, and it's going to be positive because it's just the first quadrant. So therefore we can kind of expand that out, so we'll get 6 root 3 over 14 plus 1 over, 6 over 14i. And we can kind of simplify that down a little bit more, so we get 3 root 3 over 7 plus 3 over 7i. And we probably could have cancelled out the 3 up there as well, but it's fine either way. But just make sure to cancel it. Okie dokie. Alright, so now let's talk about our Z2 cubed, okay? And this is introducing something called Demov's theorem, which is not really a part of the 1-2 study design, but it's something that you can kind of notice if you want to. Essentially what it is that if z equals to r cis theta, remember that z1 times z2 was r1, r2 cos theta 1 plus theta 2. So therefore, if we had z1 times z1, we would have r1 squared cos theta 1 plus theta 1, right? And if we kind of repeated that again and cubed it, we would end up with r1 cubed cos theta 1 plus theta 2 plus theta 3. And repeat it after and after it. So therefore we kind of get the conclusion that z to the power of n would just equal to r to the power of n cis and theta. And that's what Demov's theorem is. But essentially we can really, it's just a formula which is derived from the multiplication rule that we've already done so far. So if you do see it, you can always try and use it, but if you don't, I don't really think it's too much of an issue, especially in 1-2, but you'll definitely be doing a lot more of it in 3-4. I don't really think that you'll be solving much using this, but I think you might be using it just to kind of expand numbers like this. So it wants z to the power of 2 cubed, which means that we need z2 times z2 times z2. So we can, maybe we'll do it without just do it by multiplication first. So what that means is we'll have r2, 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 and we'll have cis theta 2 plus theta 2 plus theta 2, right? So what that will mean is we'll have 6 times 6 times 6 and cis 3 pi on 2. So that's going to be 216 cis 3 pi on 2. And importantly, beep beep, we see here that it's outside of here because it's here. So instead of writing it as 3 pi on 2, we're going to write it as cis negative pi on 2, right? And then after we kind of do that, you can also, if you wanted to convert this one to polar, it's relatively simple enough. This should just be negative 16i, because we can see that it should just fall exactly on the y-axis. Okay, so let's have a go at this one now. So what it's asking us to do is that if z plus I 1 over z belongs to r, we have to show that the modulus of z equals to 1. Okay, so let's name z equivalent to 1 plus bi, and therefore we can say that this is a plus bi plus 1 over a plus bi. Now the easiest thing to do here is try and rationalize this. So a plus bi will be equivalent to a minus bi over a squared minus b squared I squared, right? So this will give us a plus bi plus a minus bi over our a squared plus our b squared, right? Cool. So if we need this to be equivalent, right, therefore we can also apply, so if we do it this way, we can kind of see that therefore this thing would need to be like this top thing, so a minus bi would need to be rational, and this part would also need to be rational as well. And there's also another way of kind of approaching this. So there's kind of two ways to approach this. So if we kind of do this where we make everything at the top, so if we now go a plus a squared plus b squared, sorry, and then plus a minus bi, we'll eventually get that when we try and transfer that across. So the a parts shouldn't matter too much, but we'll get our a squared bi plus b cubed I minus bi, and then we'll have the kind of the real components as well. So we'll have like a cubed plus a b squared plus a. But this is the part we're interested about, right? Because if this needs to belong to real, that means that a squared bi plus b cubed I minus bi must equal to 0, right? So we can kind of factorize that in terms of b in terms of b and I. So if we try to do that, we can say that, all right, so therefore if we factorize out b, we'll get this as a squared I plus b squared I minus I, and that equals to 0, right? So therefore you'll get that you'll get that b equals to 0, or b will be equal to, so if we kind of put that across, well, we don't need the i's anymore. Just remove those because we're trying to say that it's equivalent to 0. Yeah, so this is equivalent to 0, so if we kind of just remove the i's because we're trying to say that this thing is equivalent to 0, just to make our life a bit easier. It's not strictly necessary, but it just means that we have less things to work with. So b a squared and then b squared minus b, minus 1. Okay, so that would mean that we have b squared would equal to 1 minus a squared, right? So therefore b would equal to the root of 1 minus a squared, right? So a plus or minus. So therefore we kind of can get that relationship as well. I guess the only concern with that is that if we have b equaling to the plus or minus root of 1 minus a squared, that would mean that a at most, right? So those are the two types of situations we can have. So in order for this to happen, we need b. So if b is equal to 0, that would mean that z is just simply equal to a, right? Whatever a is equivalent to. And if we look into here, right, because if b is equal to 0, that means you wouldn't really have, like you would have a complex number, but it's kind of a specific case, right? Like that's when it just literally equals to a real number. So 1 over like a real number plus 1 over a real number is always going to be a real number. It's not terribly exciting, right? But when we look at this side of it, so if we want this to also work simultaneously, what we can have here is that we know that 1 minus a squared has to be bigger than 0, right, in order for b to still be defined. So therefore a squared has to be smaller than 1. So we can kind of talk about this, well, smaller or equal to 1 can be, if we can kind of fuse it with that. And for that to be a thing, we can kind of draw out our little equation there, right? So from there, what we can kind of conclude from there is that we'll have a squared in order for b to actually be equivalent to 0, in order for like this to have no b component, it actually needs to be exactly at the graph. So technically we could say a is 1 or negative 1 in order for them to be equivalent, but otherwise we can also make this like just underneath the graph as well, right? And if we make that part underneath the graph, so let's say it's like 1/2 and positive 1/2, so in any universe, like if this was a half or positive 1/2, so let's say that's 1/2, right? Let's say a equal to 1/2 instead, we would get that this would be equivalent to just a equals to 1/2, so therefore we would have that b would be equivalent to root 3 of that, so 1/2 of that is 1/4, and then 1/4, so 3 on 4, so we'll have root 3 on 2, right? And then you notice, like, when you kind of put those two together, it will always be equivalent to that, because like when they add together, it will always give you the same number, right? Because essentially root 1 minus a squared all squared plus a squared is always going to just equal to 1, regardless of the universe. Let's talk about the other way of looking at this as well, just, for interest more than anything. So another way that we can look at this is that we can say a plus bi plus 1 over a plus bi, and then we can also say a plus bi all squared, right, over a plus bi has to equal to, or just is a thing, right, is belonging to z. So what that means is that we'll have this as a squared plus 2ab plus bi squared, right, over a plus bi, and then we kind of end up with the same thing, so we can have a squared minus b squared plus 2abi, and then we'll say that's all over abi, right? And in order for this to be real, we have to rationalize the bottom part first, and then we can go a squared minus b squared plus 2abi, and then times by a minus bi, and that will once again be over a squared plus b squared, and then you can kind of get the same thing as what we were doing before by doing a different method this way. It's always good to know different methods to do things.